I hope it's just a little delayed. Very excited to introduce our speaker for today, Professor Pierre Schaus from Université Catholique de Louvain. Special invitation here for an event organized by the Consulate of Belgium and France, and staying an extra day just to get this talk for us as well. So very excited about that. Obviously, if you know constraint programming, you know Pierre already. Did a PhD on constraint programming, later worked with Pascal in Brown University as well, and then went into industry working for Dynadec and Insight, and made his way back into academia to give this talk to you today. Has been part of many of the solvers, contributed to them, programmed them, things like MiniCP, MaxCCP, so you probably know his work already. Without further ado, let's please welcome our speaker.
Thank you a lot, Kevin. Thanks for organizing this. Thank you for the logistics. I decided to present to you this work because it's a work with someone that you know very well, Pascal, and this is why I wanted to explain what we did for this. So sequence variables. So most of you are familiar with constraint programming already? All of you? Okay, then
we have to take Pascal's
you know MiniCP, maybe you know that. MaxCCP, you know that it's just a layer on top of MiniCP, just with more functionality that we're developing. Okay. So my definition of constraint programming, not everybody will agree with it, but it's a software library with reusable components that I represent as Lego bricks. And these reusable components, they are the constraints, the variables, the search, and it allows you to declare a model declaratively to solve combinatorial optimization problems. And what you can use is a very flexible search framework to do branch and bound search, for instance, and you will rely on the constraints to print the search. Yep, this is my view of what constraint programming is about. The application where CP is very good at is scheduling. So for instance, this is a real-time optimization of a block scheduling problem, quite complex problem, the FT10 instance. And you see that in just a few seconds, you can find and prove optimality without problem. It's also very good at solving rostering problems and vehicle warning problems. Okay? Now, it is a killer application of constraint programming. In constraint programming, you should keep in mind that we don't use best first search, we use depth first search most of the time. Okay? So it's a recursive search, but you always dive the leftmost branch. Okay? This is what you do here. And every time you take a decision, which is picking a variable, fixing it to a value, you will trigger what we call the fixed point algorithm. The fixed point algorithm just asks every constraint of your problem one at a time to remove infeasible values. Okay, but you know that since you are familiar with C already. This is just different components of CP solving process. Okay, so the search will communicate with the domain store. Okay, these are the variables and all the domains, and you have all the constraints that do not communicate with each other directly, but only through the domains. Okay. Each of them will remove infeasible values. If you want to solve optimization problems with CP, it's very simple to just adapt a little bit this framework for solving feasibility problems. Just introduce a special constraint, which is the objective constraint. And this one will act on the objective variable. And every time you find a new solution, you just dynamically tighten a little bit the upper bound of your problem, if it's a minimization problem, so that the next solution that you discover is better than the previous one. And the last one that you find is the optimal one, and you can prove optimality this way. We just represented it. So every time you find a solution, you see that the next one is better, and the last one is the optimal one. And at the end, you just explore this remaining part of the solution to prove optimality. Okay, but again, I'm sure you are familiar with it, just to make sure that everybody is on the same page. Okay, so now I will focus on vehicle routing, and I will take as an example a very simple problem that everybody knows, so that I don't need to explain too long what the problem is. It will be the traveling salesman problem. Okay, that's the most simple vehicle routing problem I can imagine. The way, so Maxime, just so that you know, this problem is about you have a few cities, and you want to visit every city exactly once, but you want to minimize the total distance. Okay, it's like if you want, when you need to deliver packages like for Amazon, you want to take the shortest tool to connect all your customers. So this is a very complex problem to solve in optimization. One of the most well-known problems. The way we model this problem in constraint programming is using what we call the circuit constraint. So we will introduce one variable for every city, that represent the next city that you will connect with from that node. Okay, that's the way we model it. So one variable per node that represents the next city to connect. And the circuit constraint, we just enforce that you do not visit twice the same city and you don't have sub-circuits. Okay, the Hamiltonian property of the two. So you see, for instance, after the city 0, I go to city 2. After the 2, I go to city 1, and so on. Okay? And at the end, you've got this complete circuit. This is not so trivial to propagate this constraint and to remove infeasible values. So behind the scene, the algorithm that is used for filtering and prevent the subtours is that we will keep incremental partial chains, and we will just remove the edges that may close the tour too early. Okay? This is what we call subtour elimination filtering, and it's an idea that was invented by, maybe you know this guy, Gilles Pesan, who is professor at Montréal. Yeah, like 20 years ago. And this is still very useful. So the way to model that problem in MaxCCP or MiniCP is like that. You just introduce a bunch of variables, okay, that I call sucs, that represent the next city to visit. Okay, there one such variable per node. Then you post the circuit constraint, and then you will use element constraints to connect and compute and connect the distance matrix of your problem with the successor variable, and this will capture the distance to the next city. Okay, you just take the sum of this, you minimize, and that's it. Okay, you have a beautiful model for solving the TSP. By the way, this constraint, the element constraint, you know that kind of constraint? It's a constraint where you index an array with a variable. You know who invented that constraint? No? This guy. Yeah. So Pascal is the one who invented that constraint. It's one of the most used constraints in constraint programming. Really, but never forget that it's Pascal. The circuit constraint cannot really be used for modeling a vehicle routing problem in which you have several vehicles, right? Okay? Because it wouldn't be Hamiltonian. You have to visit this one more than once. So the trick, the modeling trick that you need to use for solving a vehicle routing problem with multiple vehicles, that you would just duplicate several times, once per vehicle, each of the depot nodes, so that at the end you have a beautiful, unique Hamiltonian circuit constraint. Okay, so that's the way we solve vehicle routing problems with CP currently. This is what everybody is doing. If you read the handbook of constraint programming, this is what they would suggest as a recipe for modeling vehicle routing problems. But there are a few weaknesses that I would like to show you with this approach. Okay, to me, one of the big weaknesses is simply this one. If you want to implement a greedy algorithm, a greedy heuristic for solving that problem, so you will start from this city and you will always take as the next customer to visit the closest to where you are. So after this one, the closest, that's a 0, you go there. Okay, and then from there you will probably go there, and then you will go there. Okay, this is an animation that shows you this. Okay, and every time you add it, you see that the objective function is increasing. But look what happens at the end. Okay, everything is fine at the beginning. Okay, this is quite good decision that you take. But at some point, you need to close the tool. And guess what? These last edges that you will add, they are very bad. Okay, you have no choice. You need to close the tool. So that's one of the weaknesses that you have. It's the first solution that we discovered by following this heuristic is quite bad, and it's well known. The other weakness of that approach is that for some problems, some of the visits are optional. And this is quite difficult to model, right? This is, for instance, price collecting trading sales problem. So you need to visit some of the customers, but you have a budget on the length, and each customer has some rewards that is attached to it. And so because of the constraints, you may not visit all of them. And this is difficult to model again because it's not a Hamiltonian thing. By definition, the circuit constraint requires that you visit all the customers and not part of it. Using as an extension of that constraint that is called sub-circuit, in which you allow to have one big circuit and you have self-loops on the one that you do not connect with. But I think it's quite artificial to model it this way. It's not natural. And the third weakness that I would like to show you is large table research. So large table research is one of the techniques that Pascal did not invent, but it made it very popular and very successful. I think that in most of the application that is solving with CP, it tries to use LNS, and probably Kevin already advised you can try with LNS. This is one of his favorite things, from what I remember. So the approach of LNS is okay. You know, local search. Local search is very good at finding quickly good optimal solutions, although you will not prove that it's optimal. And the approach is that we use CP to explore neighborhoods around the current solution. This is your current solution. It's not good at all. Okay, it's a very bad TSP. You don't want to keep that solution. So the way LNS will proceed is that it's a successor model. You will just relax some of the successors, and you will re-optimize them. Okay, you will re-optimize these very restricted products, but the other edges you keep them fixed as they are in the current solution, and you repeat that with a few random relaxation. And you will see that this way we were able to improve quite well the solution. So just to show you how it works. So you relax, these are the red nodes, and you really, that's your only degree of freedom is reconsider the decision that you have taken from these red nodes. And you see that this way we are able to improve the solution. It's very efficient at finding quickly good solutions. But still, you will see that the solution that you're able to reach with by relaxing 5 successor variables is not that good at the end. And the problem is that we don't have so much degree of freedom to re-optimize the tool with this successor model. Okay, I'll let it continue. You see that this is quite close to the end, and it's still not that good. Okay, I would need to relax way more variables to be able to escape from this local optimum. So these are the 3 weaknesses of the successor model. And so what I want to propose is that instead of using the successor of decision variables, we should instead try to have a strategy for finding the first solution that is based on insertion of nodes inside the partial tool. Okay, and this is what I will do here. So what I will show you here is that we will have the partial tool. Okay, initially I think just connecting the node 1, 0 with the one that is the further away, so 21. And then every time we will take the insertion that will maximize the length of the tool. It seems counterintuitive, but it's very good. Look at what the behavior of that approach. Okay, so you take the one that increases the most the partial tool. Okay, and if you do that until you have inserted all the nodes, you will have a very beautiful tool to start. Okay, it's much better than the closest neighbor strategy. Yes, that's a tool that will obtain at the end, and you see that the objective function is reasonably good. Okay, so this is based on insertion, and this was really the starting point for us to say we need a new kind of variable to be able to do this very easily in CP and make this approach complete. Because this is not complete, right? This is just a purely heuristic greedy algorithm, but we will try to make it complete. And if you do LNS with this approach, you will see that the local optima that you reach is much better. Yeah, this is the objective function that we had with the successor variable. So now I will show you what it gives if you use the insertion sequence variables. Okay, so in red you see that with the same amount of variables that are relaxed, but I allow it to be reinserted in the tool, we are able to escape much better from local minima, and it is also decreasing faster. Okay, so I hope that I convinced you that insertion are very important in CP, and the successor model does not allow it easily because it's not built this way. So what we will do instead is that we will have a new sequence variable, and this variable represents the path, not a circuit, but it's just a path. And this path is never empty. It has always a beginning node and end node that I call alpha, omega. And what this constraint will allow us is that we will gradually be able to extend this partial path by inserting nodes in the middle of 2 nodes already in the sequence. So here we will insert V2 in the middle of alpha and omega. And so the partial circuit that you get after is represented here. The gray edges that you see here are the feasible insertion that are still possible inside the partial tool. For instance, if I have this edge and this edge, means that V1 can still be inserted between alpha and V2, and so on. So after that, I insert V3 between alpha and V2. I've got this partial tool. Okay. So this is a variable that is really designed to allow insertion. And so the model for modeling the TSP with sequence variable, you create a sequence variable like this that represents the tool, You give it the start node, which is alpha, and omega, which is n. Okay, so the size is n plus 1. And so I will artificially duplicate here the beginning and the end node. I post a distance constraint, that is a constraint that I will explain later, that is designed to work with sequence variables, and then you minimize the total length. And this one will make the connection between the distance matrix and the total length. Okay, so the model is also easier. And if I want to solve that with LNS, with large level search, it's super natural to do it. Okay, this is your LNS loop. So for a number of iterations, 100 in this case, what you will do is that you will randomly select a subset of 5 nodes among the n nodes from 0 to n. I call them a set of relaxed nodes, and you will just post this partial relaxed sequence constraint to say, okay, out of the current best feasible solution, I would like that to relax this node. But for the rest, keep the partial sequence as it was, the current best solution. Okay? And if you do that, you will have the behavior that I showed you before. And so just intuitively, this constraint, this relaxed sequence constraint, if this is your current best solution and you relax these 2 nodes, you just remove them from the partial sequence. Okay? And it will be possible to insert transfer. This one here and this one. Okay, let me define a little bit more formally what the sequence domain is about. The sequence domain is composed of 4 different types of sub-constraints. I don't know if you know set variables in C. Set variables? Set variables is also a kind of computational domain, or in which you have sets as the final values for the variable. In set domains, you can have required node, and excluded nodes. Here we have the set. You can ask this node I want it in the sequence. It's not an excluded, but I don't know. An excluded node. I say this node is forbidden in the sequence. I don't want to see it. You have a global subsequence that is required to appear in the final sequence. And you can also impose that some nodes cannot be inserted between triplets of nodes. Okay? This is the 4 components of the domain. And this will be very useful for filtering the domain. For the global constraint, we will use it. Don't worry, I will explain that to you one by one. So if you want, for instance, at the beginning, since it is a sequence domain, the set of values are all the possible sequences. Okay, so if I have, let's say, 5 nodes, alpha is the beginning, omega is the end. These are all the possible sequences that you can represent with the domain, right? So now assume that I ask V2 to be part of the sequence. It means that only this one will remain part of the domain. And implicitly, this one will disappear because it does not appear in the sequence. Okay. So in addition to that, if you say that V3 is excluded, then some of them will disappear, right? All these ones are not part of the domain. Take the intersection. This one, this one, this one. If you ask that this is a subsequence, alpha, V1, omega, but maybe with other nodes between, okay, you will only keep this one. Okay? So you take the intersection of the 3 constraints. And finally, you can also require that, for instance, V2 is not between alpha and V1 is not between V3. Okay? It's a root string further the domain. And so at the end, okay, see that, and at the end, the real domain that's represented with these 4 constraints is the intersection of 3. Okay, so you project intersectors. At the end, you have only this one, the feasible sequence for that representation of domain. Okay, so formally, the domain again is composed of these 4 components: the required nodes, the excluded nodes, the partial sequence that needs to be in the sequence, and the forbidden in between triplets. Okay, and implicitly you represent every sequence so that T is an alpha omega sequence. The required nodes I need. The one that excluded are not part of T, as this one is a subsequence of T, and the node between constraints are satisfied. Okay. So what you can realize is that if I naively represent and implement this domain, How much memory do I need? Expressed in terms of number of nodes. Well, you will see that it's cubic, right? Because simply because of this forbidden not between constraint, you will need cubic amount of variables. There's the triplets here. So n times n times n will be cubic. And so to avoid a cubic behavior that will be catastrophic, you know that there's a big difference between cubic and quadratic. Quadratic is not. Well, it can be scalable up to a few hundreds, but cubic, even with 200, it will kill the speed of your solve. Okay. So to represent it, we will have a very nice implicit domain representation that we call the graph. We use a graph like this one, and this one will encode all the possible insertions. Okay. And so we have a very nice data structure that are using sparse sets, which is reversible so that it can restore itself on backtrack. That's the way we implement them. I will not enter too much into the details. You can read the paper if you want, but we also have a reversible data structure to represent the partial part, okay? The one that must be included in the final sequence. And we will also maintain dynamically the number of possible insertions of every node with respect to the current sequence, so that you can really use that to implement heuristic search. Okay, let's speak about branching, because so far I've just explained the variable. Now I will explain the search component on top of the sequence variables. So you know that in CP, there are basically 3 different ways to implement complete search. This is the one that is the most used. You pick a variable, you pick a value, you say on the left, this variable is equal to the value. On the right, you remove that value from the variable. You also use sometimes this split of the domain. So you pick a value, you say on the right, they are larger than V and less or equal than V to the right. Okay. I said that it's a binary branching scheme. And here it's the n-ary branching scheme in which for every value inside the domain, you try it for every value, okay, out of the variables that you're seeing. I will try to make it similar for the sequence variables. So for sequence variable, if you want to implement this in the same spirit, what you would do for the sequence variable is that you would pick a node V. You would pick a node in the middle of the partial sequence, Vk, and you will say, I will insert the node V just after that one, on the left branch, and on the right branch, you will say, V cannot be between Vk and Vk plus 1. You exclude this insertion, okay? And this way, if you implement that, you will remain complete. So this is a kind of search strategy that you will implement over sequence variables. If this is what you want to do, then you would do it differently, right? You will say, V cannot be between alpha and Vk, so you will exclude insertion from the first part of the sequence, and on the right branch, you will exclude the second part of insertions. Okay, this is pretty simple. And if you want to have this, then you will try to insert the node V that you have selected at every possible location in the partial sequence. Okay, so these are 3 branching schemes that you can use for sequence variables. I don't know which one is the best. Okay, we didn't experiment it that much. But to me, if I need to make the analogy with integer variables, this is what you can do with sequence variables. Yeah, just to make sure that you see what I did. So if you want to insert V2 that you have selected, on the left branch, you will select, for instance, the insertion after alpha, and on the right branch, you prevent the insertion. And if this is an n-ary branching that you want to do, you pick V2, and you try to create one search node for every possible insertion. Okay. Maybe you could ask yourself, why don't you branch on the nodes that are not yet inserted as alternatives? It's because if you do that, that would be valid. You would have a complete approach. But unfortunately, you will introduce many symmetries. Okay. You will not completely split the search space in 2. Okay, and there is a possibility that we discover a sequence that was already considered by exploring another part of the session. This is why we don't use this scheme for branching in sequence variables. The first thread principle. You are familiar with that one? Okay, it's a principle that we use all the time in CP for the variable selection. Okay, this principle was introduced a long time ago in a HDI conference, and it says it's very counterintuitive. I know that it says, to succeed, try first where you are the most likely to fail. Okay, that's the essence of this principle. And if the way we implement this principle in CP, a very simple way is, for instance, as an X variable to fix, pick the one that has the smallest amount of values in its domain. Okay, because that's probably the most difficult one, the most critical one to decide next. If you want to fail early. And it's quite natural, right? If this represents your search space and you have some hard to fix variables and easy to fix variables, the way your search tree should look like is like this. Okay, you first want to fix the hard part of your problem early in the search tree, and you will keep the easy one at the end. Okay, this way you will have a small search tree. If you do the opposite, you have the risk to have a very large search tree. So the first strategy of integer variable, again, it's just to pick the smallest domain size. What does it mean for sequence variables? Well, for sequence variables, let's assume that you have two nodes that can be inserted into one partial sequence. This one has two possible insertions. You can put this one between and this one in between. Okay, while V4 can be inserted at three different possibilities between alpha V1, between V1 V3, V3 omega. Which is the next one that you decide to choose for the insertion? You prefer to insert next V2 or V4, according to the first rate principle. So again, this one has three possibilities of insertion. This one has only two. V4. Actually, no. You prefer V2 because it says. That's what I mean. Okay. Thank you, Maxime. This one has only two possibilities. So the first rate principle says, try first where you are the most likely to fail. Since you have only two possibilities, you should prefer V2. Okay. You know that in CP, we use depth first search. What it means for optimization problem is that the first solution that you discover on the leftmost branch should be good. Because if it's good, it means that you have a good primary heuristic and it will be more efficient for the pruning by the corruption bond. Okay? And so what it means is that we should also keep that in mind when we implement heuristic on top of sequence variables. And I will show you the code how we keep the two IDs together. Okay. So for my TSP, for instance, what I could do is that I will select as the next node to insert the one that has the smallest possibilities in terms of number of insertion. I call this node time. And after that, I need to decide where I will insert this node. And the insertion place location that I will select in the current sequence is the one that reduces the most the increase of the length of the partial sequence. Okay. This is the two edges that you will add due to the insertion of that node in the middle of the partial sequence. And this is the edge that you remove. Okay? And I will try to, the next insertion, I will choose the node to insert after the node that will reduce the most augmentation of the distance. I was not super clear. You get the idea? So I try to select the location for the insertion that impacts the length increase of the length. Okay? On the left, I insert this node. On the right, I remove this insertion. This way I'm confident. So first failure principle, very good primary heuristic. You can have both. Okay, and the final topic that I wanted to discuss with you is how to implement constraints on top of sequence variables. For that, I will choose a very simple one, which is the distance constraint, the one that we have used for the TSP. So again, it takes the sequence variable, the distance matrix, and the distance variable. Okay, and so this variable just represents the total length of the sphere. So the way we filter it is two things. First, we will update the lower bound of the distance variable. And what we'll do, because you know that it's a very hard constraint, right? It's as complex when it comes to domain consistency. It's as complex as solving the TSP. It's an NP hard complete, an NP hard constraint to filter. And so we will do a relaxation. And what we will relax here is that we will not take into account the inheritance. We do LCP, but not required. Okay. So we will say that the lower bound of distance is just the length of the partial path. Okay. And then for every possible insertions that I have here, okay, for every possible insertions, so for every node in the sequence, I get all the insertions that I can do after this node. Okay. And I will compute the cost, the delta cost that I would have if I would insert this node just after that node. if the increase of the cost is less than the maximum slack that I have with respect to the maximum upper bound of the distance variable, I just say that this node cannot be between this one and this one. And I remove the insertion. Okay? And so you can really design beautiful filtering algorithm for that computational domain, as you would do for integer variables. Okay? And to me, this is just the beginning, right? There is plenty of constraints that remain to be invented and plenty of filtering algorithm. So it's a very nice research topic to work on filtering algorithm for this kind of intervals. Okay, so just for the illustration, if this is your partial path, okay, the lower bound will be the length of the blue path here. And this one, for instance, we say, okay, if this insertion, okay, the cost of adding the red edges minus this one is too large with respect to the maximum length allowed by the slack that you have, this is a slack, you just remove and cover this insertion. Okay, so we have a bunch of constraints that are quite useful that can use for the model, but there are many remaining constraints that you could do. You have the transition time constraint that allows you to quick pause time in the constraint. You have the precedence. You have a cumulative constraint that is very useful when you have pickup and delivery problems. When you have pickup and delivery problems, most of the time you have a capacity on the vehicle. Okay? And at some customers you will load, and on some customers you will discharge it. This one allows you to model this kind of problem in vehicle modeling. Okay? Just to show you two more, slightly more complex problems that we have solved with sequence variable. This is a TSP with time windows. Okay, it's the same as a TSP, except that you have time windows that you need to satisfy for the visits of your customers. Okay, you can use sequence variable for modeling that problem. Okay, it's quite efficient. And you can do LNS as well. If you do LNS for that problem, I advise you to not relax randomly as I did for the TSP, but you take the partial sequence and you will just take a window in the middle of it, and you will re-optimize that window. And of course, you randomly select the window. Okay? This is very efficient to solve the problem with this. And with this very simple approach, we were able to improve. I think I have the results here. We were able to improve 2 or 3 years ago a few of the best known solutions on a famous benchmark of the TSP-TW with this approach. And if you model that problem with CP, it's a little bit less elegant, right? But the way you would model it is that you will introduce one variable per node, and xi just represents the node that is visited at position I. Okay, and you move like this. And again, you will use element constraint to enforce the time window constraint, and you will use also element constraint for computing the transition with respect to the next city that you will visit at xi plus 1. Okay? Again, this is an illustration that the element constraint of Pascal is very useful. Okay. And the sequence model is, I think, much more intuitive to understand. You just have the tool. You say that every node is required to be visited. The time window constraint, you have them directly modeled by the transition time constraint. And you have the distance constraint for computing the total distance, and you minimize the total transition. Okay. If you use LMS, you will succeed at finding very good optimal solutions easily. Pickup and delivery problems. This is a problem where you have some nodes that are represented like this one that needs to be delivered at some other place, right? So you have pickup nodes and delivery. And you need, okay, we call that a request. So request is composed of 2 nodes, a pickup and a drop. And you need to find the optimal way to satisfy all the pickup and drops. Okay, and you have a capacity on the vehicle. And so if on top of that you have maximum write time between the pickup and the delivery, we call that a real write problem. Okay, it's used a lot for on-demand traveling. Okay. The way to model that problem with sequence variable is that you will introduce, and you have multiple vehicles as well. You will introduce one sequence per vehicle. Okay, and you will minimize the total distance, the sum of the distance over all the vehicles, the k vehicles. Then, for every vehicle k, you need to pass the distance constraint. You have to compute its length. You have the transition time constraints. here because you have time windows within which you need to pick up the customer. And you have a cumulative constraint to make sure that you do not exceed the capacity of your vehicle. And finally, you say that every customer is visited exactly once. Okay, you cannot have two vehicles. Okay, and that's the maximum high time. Okay, constraint.
Is there no precedence between the pickup and the lift?
There is a precedence, and I think the precedence is enforced.
Or maybe your time windows.
Already enforced here, and maybe with a transition time. That's a good question, too. No, you know where it's enforced? That's a good question. It's not enforced by the model. It's enforced by the search that I will show you.
Okay.
That's a good one. Because we do not enforce it in the model. Okay, we use the search. You will see it's a very nice search. Okay. And the search will do something. You know who invented that search? Pascal. So this is also a good illustration. I think I did that a few years ago. It's a search in which you take the pickup and the delivery node. So you take the two nodes of the request, and you will enumerate all the possible insertion of that request inside the sequence. Okay? And back before that, you will set the pickup before the delivery, the sequence, so that the precedence constraint is satisfied.
I see.
Okay? That was the nice idea of Pascal. But Pascal didn't invent the sequence constraints. It was done, I think, with standard CP variables. But with sequence variables, it's much more elegant to solve and to implement this search. And this is the paper of Pascal that has given us the inspiration of implementing the sequence variables, because we found that this search was so elegant that we wanted a very nice variable to do it easily. And so this is what the search is doing. You take the request. Again, it's perfect. You take the request that minimizes the number of insertions for the pickup multiplied by the number of insertions for the delivery node. Okay? So it's a double force function for the pickup and delivery. And then you will try to see you have a double for loop for inserting first the pickup and then for inserting the delivery node. And you will branch by inserting the two nodes at once. Okay? So one branching decision is inserting the pickup and the delivery node. Okay? So there is quite a this search has a large branching factor, and if it is too large, what you can do is reduce a little bit the branching factor by using, for instance, discrepancy search. You know what the discrepancy search means? Okay. It just means that if you sort the branches increasingly by some heuristic, let's say the detour distance, you will only consider the few first branches and not all of them for your branching. The rest you will drop them. Okay? Of course, you will not be complete, but this is what discrepancy search is. Okay. And the results, well, we compare here with off-the-shelf solvers, right? We have Exali, OR-tools, and CP optimizer, and our successor-based model also implemented by CCP. And what we have seen is that the sequence variable approach was much better in practice. Okay, we were able to get a smaller primary gap. So we reach better solution as using sequence variable. And it's quite logical, right? Because the other approaches, well, this one, you know that it's less flexible. OR-tools has a different kind of sequence variable. It has also sequence variables, but it's completely different. I will show you. So they don't have the insert in the middle. They have something instead that maintains the prefix of the sequence, and you can only append something at the end of this. Okay? It's very nice because in terms of memory, you consume less memory, but heuristically wise, you are less powerful because you don't have this possibility of inserting something in between. Okay? This is why if you have, I would say that this is the right approach if you have thousands of nodes to optimize. If you have a few hundred nodes, the N squared is probably better, better flexibility. very smart insertion in the middle. Okay, so I don't say that one approach is better than the other one. It really depends on the size of your problem.
Is this so? Do they have sequence variables, or is this what they do in the routing library?
This is what they do in the routing. So in conclusion, sequence variable, I think it's a very interesting computational domain for CP. I'm super excited about it. You have constraints that are targeted for making routing problem. And the search space, remember that it's by inserting nodes in the middle of the partial CPs. Okay? And it's also very nice for the because it's very natural, relax by removing some nodes out of your solution and reinserting. So feel free to play with the domain. Everything is open source. Okay, there is a paper that describes a little bit this computational domain. And that's it. Thank you for your attention. Thank you for attending this seminar. And thanks again for the invitation.
Thank you. We have questions for our speaker.
You didn't check the time.
I mean, I'll go first. Think of more questions. So I'm very curious because in my PhD, I worked a lot of vehicle routing, but that was more on the integer programming side, right? Column generation, that kind of stuff. I'm very curious how you see the advantages of both approaches, because MIPS are very good at solving TSP, for example, but I can imagine if you make it complicated enough, you're going to win with CP, or maybe you'll tell us you always win with CP if you do it right.
No.
So I'm just very curious how you
never,
look at this.
I will never say that, right? But I think MIP is super powerful, but you need a lot of expertise. For instance, if you implement advanced branch and cut things, because for instance, if you take the circuit elimination constraint,
yeah,
it's a branch and cut that's used in MIP. And so it's not declarative. This approach is more declarative. I think you can make it used by someone who has less expertise. It's easier to do. But it's also very flexible to do if you do LNS. You can really implement nice ideas on top of these sequence variables. For the column generation, it's also the same, right? You cannot, it's a quite advanced technique, right? You did your PhD on that.
Yeah.
But for some application, you don't want to have a PhD for some application. And you use column generation, but not branching price. Oh
no, I've used branch and price and everything.
Okay, you did everything. So you were using column generation at every node?
Yep.
Okay, so that's very advanced, right? You don't have an off-the-shelf solver that is doing that. You need to do it manually.
Oh, I know. It was programmed for months.
Yeah, so it takes a lot of time. So in terms of software engineering, I think this one is easier to solve, and it might be a good compromise. It's also easier when you have a model that is changing. You say, okay, can you please add this new constraint? Okay, it's quite easy with software. With branch and price, you may say, wow, it doesn't work anymore, right? What am I doing? Okay, I need to find new column elimination constraints. So it's not very adaptive. One of the strengths of CP, and not this one in particular, that the models are adapted, easily accommodate new constraints. I think that's the beauty of CP. But I will surely not say that this is works. You could use that for the pricing in column generation, right? For some pricing problem, it might be interesting to use a sequence variable just once. So I strongly believe in hybridization of techniques, and I think it might be useful for column generation as well.
Great, very interesting.
Or scalability. Yes.
So have you done a performance comparison between your approach and MIP and like how the solution quality changes within the same amount of solution time and instance sizes?
Yeah. You mean for the TSP?
Yeah.
For the TSP, we are not good at all, right? We are not good at all. We do not aim to solve the TSP, and we will never be able to solve the TSP as well as the MIP. I took that example only for the sake of teaching you what sequence variables are about. But for the TSP, no, don't do that because the lower bound is very weak. What I'm doing here with the distance constraint is super naive, right? But there is still a lot of MIP techniques that we could embed exactly by constraint. This is what people do all the time. So I think in CP, what we do for the TSP, for example, that we use a hand and pair polarization inside the global context for pitching the domain. We need to do that for sequence variable as well. We didn't do it yet, but that's part of the plan to do.
Pascal, great timing. Are you doing questions? You will answer like 5 minutes. Okay, anyone? Let's give them a random.
Pascal, I've shown a few pictures of you.
Because I'm so weak.
Is it one of the slides? It's a picture. Look, Pascal, this is you.
This is me? Oh, wow. There is a question on that? I don't even remember.
There was a nice question of Kevin that I couldn't answer. He said, how do you deal with the precedences between the pickup and the delivery nodes? I said, I don't know. And then I remember that it was a search of us. It's done by the search.
You insert it inside the search of the same.
Yeah, inside the, so you do not add the precedence constraint between the pickup and the delivery. You enforce it during the search.
That's right.
Yeah, it's also like one.
Okay, going once, going twice for final questions. Let's thank our speaker one more time. Thank you.
So one question for you. Who did invent the element constraint?
This guy?
You know the something.
You know what's the
The
question?
element constraint.
Yeah.
I said that you invented it.
Yeah.